In this video, we are going to see about the analog to digital converter ADC and digital to analog converter DAC. And first we see what is the necessity of ADC and DAC. Most of the real world quantities like voltage, current, temperature, pressure are in the analog form. So the analog quantities are difficult to process, store and transmit. Even though it is accurate, it is difficult to process, store or transmit because of the noise present in the analog signal. Therefore, for processing, transmission and the storage purposes, it is better to express in digital form for the better accuracy and the noise reduction. So we are going for the ADC and DAC. First we see what is DAC. So DAC means it converts the digital data into its equivalent analog data. So here this is the DAC. Here input is digital signal. So B1 to Bn are the bits, the digital data. So this will be the binary data. Here n bit data. So n bit digital data. This is the LSB and here it is MSB. That is converted into the analog data by using a DA converter. And now here the output voltage, the analog voltage V0 will be Vk Vfs into B1 to power minus 1 plus B2 to power minus 2 up to Bn to power minus n. This V0 is the output voltage and K is the scaling factor. It's usually taken as 1. This Vfs is the scale range of the voltage. And then B1, B2 are the n bits going to transfer. So this B1 is the MSB, most significant bit, and Bn is the least significant bit. And now we move on to analog to digital converter. So here it is the inverse of DAC. It performs the inverse operation of DAC. It converts one analog signal into its equivalent n-bit binary coded digital output signal. So the digital output from an AD converter can be in serial or parallel form. Serial form means the bits will come one by one. Parallel form, at a time all the bits will come. Here these converters are divided into two types, the direct type AD converters and the integrating type AD converters. So the direct type AD converters, it compares a given analog signal with an internally generated equivalent analog signal. Internally an analog signal is generated and the given signal is compared with that. Accordingly a digital bits are generated. The integrating type of the AD converters, it performs AD operation in an indirect manner. So in the ADC we are going to see about one direct converter, successive approximation analog digital converter. So in this type of ADC, it consists of one successive approximation register SAR, and this register SAR creates own bits. When a clock pulse is given, an approximation of bits are generated. It will occur when the start bit is 1. If the process ends, means this AOC, end of conversation, will be 1, then automatically the process is over. That is the meaning. And here the generated bits are given to the DAC, digital to analog converter. So here this digital analog converter converts the generated bits into analog signal, and this is the analog signal VR. Vi is the input voltage. We are going to the voltage we are going to convert, that is Vi. This is the analog signal we are going to convert, that is Vi. That is compared with VR, that is generated voltage. Here this part is this IC is used for a comparator, and then if Vi is greater than VR, then it will generate 1. And then when both are equal, it will be 0, then the process stops. And now here this B1 is the MSB and B8 is the LSB. Now see with the example. First, initially this SAR generates B1 as 1 and the remaining things as 0. B1 1, remaining things 0. So B2 to B8 0. Okay, so 1 0 0 0 0 likewise it will be. And now this 1 0 0 is converted into an analog signal that is given here. Now the given, it is compared with the given signal, analog signal. If both compared, if this value is greater means here you will get 1. That means again this value is greater, so the generated value is very smaller. It is not equal to VA. So now here again if it is this VA greater means the B2 will be 1. So 1 1 0 0 0. Again these bits are converted into digital to analog. Again that is compared with VA. Till if VA is greater means, and then the next bit will be 1. Suppose if VA is lesser means, then this bit is changes to 0, the next bit will be changed to 1. Likewise this process repeats and finally you will get the correct digital value, the equivalent of this VI. Now we will see with an example. Let us take this as the VI, the equivalent of this analog signal. This is taken as a digital value. So if you want to convert that analog to digital, you have to get like this. For that initially SAR will generate on its own. For that this B1 bit is 1, the remaining is 0. And now it is compared with this. Now we don't know this value, the analog signal only. Here this digital is converted into analog, and now we are getting this value is greater, since this is 1101, this is greater. So if it is greater, VA is greater means, then automatically the next bit will be 1 and the remainings are 0. Now these two are compared. And then here when these two are compared, this will be greater. And so again the next bit will be 1, the remaining are 0. And next these two are compared. So if these two compared, if it is greater means, then you will get 1. If 1 is present, the next bit will be 1. So again it is compared, so the compared output is 1. So again the next bit will be 1. And then while comparing these two, here this will be greater. It is not greater, then it will generate 0. So if it is 0 means, here the comparison, automatically what will happen, this third bit will be changed to 0 and the next fourth, this bit changes to 1 here, and next again the remaining are 0. And now while comparing these two bits, now it is greater. It is greater means here the output will be 1. The output is 1 means the next bit of this, here it is 1, the next bit of this will be 1 and the remaining are 0. Now these two are compared. While comparing these two, here now this is greater, now it is 0 is generated. If this is greater means the last we have changed one bit, no, that bit we have to change it to 0. Again the next bit we have to change to 1, then 0 0. And now while comparing these two, here this is smaller and here this is greater. So again here getting 1. And now here again, so we have to add 1 1 and then 0. And then again it is compared, and then if it is lesser, then 0. Again it is compared, here 1, so 0. So 0 means what you have to do, you have to change it as 0 and then next as 1. So the finally we attain the same value. So we got the correct output, 1101 01 00, 1101 01 00. So we got the final output. Then EOC, that is end of conversion, is 1. So we got the correct digital value. So that is the final output value. So the digital, the analog to digital converter is just approximated by using these 8 bits. This is a 8-bit ADC, since number of bits used are 8. So here the conversion is given. This is the output response waveform. So here the correct digital representation is here. The equivalent decimal value is 212. So this is the 212 point and it is represented like this. So initially it is, this value is 128. So here it is 128. Next 128 plus 64, that value is here, 192. Then again plus 32, that is represented here. Likewise we are finding. So finally we are getting the value. This is the value. That is, this is VI, the input analog signal. Now we are generating the equivalent binary value here. So finally we reached that value. So next, the next analog signal. Likewise we are getting the output response. So now find this analog signal is converted into digital. So these are all the explanations present here.